Hello everyone, we are going through the fourth video of our series. So today we will talk about scenarios. Like ideation, it will be a lot of explanation and scheme to discuss. So our producer at Kado is Jagannath. Jagannath, welcome.
Glad to be here. So, in order to build a complex solution, you need a set of techniques that are connected together to achieve the objective. But to get that, you need to start with tasks and then methods. At Kado, we show you how to do all three. Let's get started. Okay, let's do a quick recap of where we're at and how we got there. Firstly, we took the problem, okay, and we came up with this flow of tasks. We started with the objective, which is the preventive security engine, and we worked backwards, step by step, all the way to the inputs. So this is a flow of 9 different tasks that we want to perform in order to solve this problem, and it's still at a very, very high level. So next, what we did was we worked forwards for each of these tasks, and we identified the specific method that will be used to solve these tasks. For example, with feature extraction, right, we said we will be using computer vision to identify the prominent features in the face, and then we'll store those features in a serialized form in a database. Okay, so what does that mean? So that's still a little high level because methods and method families have many techniques inside them. If we are talking computer vision, for example, scale invariant feature transform could be a technique that we apply, and that is going to be one that we're going to use here. If we are talking supervised learning in machine learning, as an example, then there's techniques like support vector machines, logistic regression, decision trees, XGBoost. These are all techniques. So that's the level that we want to get to in this exercise, because the specific configuration of these things, right? So XGBoost may have different flavors in itself. Like I know that regression, if you take regression as an example, there's ridge regression and other different flavors of it. Those kinds of choices we don't need to make at this stage. That will be done in the subsequent phase in prototyping and assembly, and it's better to do that hands-on when you're working with it. All you need to do at this stage is to identify the specific technique that you're going to apply to solve a particular task and in this particular flow. Okay, so let's get started. The first one we're going to look at is feature extraction. We're going to see 9 of these. For each one of these, we'll first do a quick recap of what the method flow looks like to remind you from the prior session. Okay, and then we'll get into what the specific techniques are and how they're going to work for that in that method family. Feature extraction. Let's do a quick recap. What we said is we're going to extract and mine images from access control systems that's available in buildings. And then from these images, we identify and pull out the prominent features in the faces, okay, serialize them, and then store them in a database. And that's the method for the feature extraction task, right? How is that going to actually work? We're going to rely heavily on classical computer vision techniques for this. So specifically, the one that we will use is the scale invariant feature transform, or SIFT. And that's the first step. It's used to identify prominent points in a face. Next, we obtain morphometric vectors. So these are vectors that are used to represent fiducial features on the face, like contours and so on. To obtain these vectors, all you need to do is run linear regression, and you can obtain these. Next, you take these vectors and then you reduce them. You do dimensionality reduction using techniques like PCA or tSNE, and then you use the reduced representation as the index for the content. Okay, so the content is the morphometric vectors, and the index is the reduced representation that's obtained from PCA or tSNE, right? And now what you do is you take these two things and then you put them into a biometrics database. So any image database that allows for content-based image retrieval. IBM's QBIR is an example. I think that's proprietary. I'm pretty sure that's open source versions as well. So any image database that allows for content storage and content-based image retrieval, we kind of want to use that as the information system and database at this stage. And that's the task of feature extraction. We were very high level before. Now we've narrowed down the scope quite a bit, and we are fairly specific as to what we want to implement. Next up is regulation extraction. To remind you quickly, you will have rules and regulations and laws and guidelines for buildings. This should be available in a digitized form. All you need to do is extract that. So the concepts, the classes, and how they are interrelated, and create an ontology. And to do that, you also use natural language processing to assist with the creation of the ontology. This effort should be overseen by a human expert. Okay, and once it's done, you have this information and you can load it into a system that supports ontologies or lets you manage ontologies. That's the high level. Let's see what it looks like in detail. The first part remains the same, which is the source. It's the rules of the regulations. Now you want to extract this information using NLP. But in order to create an ontology, you first want to define the classes, the concepts, and their interrelationships. For building regulations, you may want to just start with the table of contents, with the chapter headings, the section headings, and so on, to get an idea of what the regulations are about. And also in the body of the regulations text, using NLP, you can surface concepts. Okay. There could be classes and concepts with relation to constraints. So stuff like corridors cannot be more than 5 meters wide, could be a constraint. So there could be constraints in there. It's also going to be hierarchical relationships. So a building has floors, floors have spaces. There could be common spaces. There could be restricted spaces. So this taxonomy of how everything works in the building. These are the sorts of things that you want to extract and that you want to model in the ontology. We mentioned natural language processing. That's important, okay? But ontology creation is a manual task. NLP only exists as a support mechanism. Once you extract that information, an expert, a human in the loop, should supervise the creation of the ontology, okay? The classes and concepts and interrelationships is the first step. Next, you actually want to model individual rules. Individual rules. So again, NLP extracts them, okay? But the creation of the rules, so what a specific rule, it concerns which classes, at what level, how they're connected together, what that rule is, that definition, right? Has to be done by, again by the human user, but the NLP engine can be used as the starting point. It could be used to extract the stuff and surface it, and the person creates the rule based on what comes out of the NLP engine. The output, the ontology that's created, you can use any system that supports ontologies. Okay. Now, there used to be one called Kraken. Now it's called TypeDB. I don't have any connection with them. It's a system that supports ontologies. As an example of a knowledge base or ontology, there are many others in the market, okay, open source and proprietary. Go and take a look, and you should be able to find them. Okay, so that's regulation extraction. Next up is person detection. This is actually quite straightforward. There's video feeds, right, in common areas, in restricted areas. So CCTV, extract that, use computer vision to detect persons. How does that work? The computer vision pipeline has 3 steps. Firstly, you detect changes. That could be as simple as looking at the pixel values, right? If the pixel intensities change beyond a threshold, then that's a change. Step 2 is foreground, background segmentation, right? And then finally, you can perform object tracking using a HAR filter. All of these are classical computer vision techniques, and that's what you use in step 4, person detection. Next, we have pose identification. Here, we take the output of the person detector and we use that for pose identification. Also, there's historical training data that can be used for this purpose as well. The process itself uses a combination of computer vision and machine learning. There's 3 steps. Firstly, we want to detect joints, we want to estimate the skeleton, and we want to characterize the pose. So this is like using those stick figures that you may have come across while encountering gaming or special effects, right? So the stick figures that approximate a skeleton, that's what we are creating here. That's what we are working with. Okay, so these 3 steps, which is detecting the joint, estimating the skeleton, and characterizing the pose, the idea is to use stick figures to do those steps. How does that work? Okay, detecting joints. We're going to use a combination of the spectral graph wavelet transform and a hidden Markov model to identify joints. We're going to use a multi-level HOG or histogram of oriented gradients and a support vector machine to recognize the skeleton. And then finally, we're going to use an LSTM to characterize the pose. Any model with memory would do. LSTMs are just classic for that. So we'll just use an LSTM for that purpose. So detecting joints, estimating skeleton, characterizing pose. That's what pose identification entails. Next is cloud modeling. We saw this before. It's got a few inputs, the logical representation of the spaces and connectivity from the building model, the output of the person detector, and any sensor data that's not video feeds, right, like motion sensors, other types of sensors. In video-free areas like toilets and locker rooms, we use that as input. And we do 2 things. One is a discrete event simulation to model a crowd. And then we also do some pathfinding. So about pathfinding, in the previous session, when we were talking about it, we said if it's a large facility, very complex, lots of scenarios, lots of functions, right? It might be better to pre-process pathfinding as part of step 2. Note, we didn't do that here. We are making an assumption to simplify the problem a little bit, that pathfinding will be done here in step 6 and no pre-processing in step 2. Okay. Also, the other thing that we said in the previous session was that step 6 will be a discrete event simulation, whereas step 7 will involve an agent-based simulation to model behavior. Okay. So as part of that, we need to run a behavior design intent model as a pre-processing step here in step 6. But it's a pre-processing step for the agent-based simulation in step 7. So we'll see what that looks like. The building model, we said use ETL to create it. This just shows that detail again. Again, we saw person detection, the 3 steps with the change, detecting the change, foreground, background segmentation, and the object tracking. We're just repeating that here. And then the output from all these things, right, and the motion sensor input comes into the crowd model part. Firstly, we use a discrete event simulation engine to do the simulation, right? SymPy is an example. Any logic is also an example. I believe that one is commercial, right? All of these are just examples. And then the other part is the solver, where you do pathfinding using A star. And then, like I mentioned before, a BDI agent model. It's a pre-processing stage. It's prepped for the agent-based simulation that you'll see in the next step, which is step 7, behavior model. This is what crowd modeling looks like at the detailed technique level. Behavior modeling, this is the high-level flow, right? So the behavior modeling step takes as input the data from the pose identifier. There's also historical data that's used to train a machine learning model inside it, okay? But as we discussed before, step 6, we run a discrete event simulation. And in step 7, we perform the agent-based simulation. In step 6, we also do some pre-processing for step 7. So let's see how the detail looks. Step 5, we had 3 parts: detecting joints, estimating the skeleton, and characterizing the pose. The outputs from these are fed to the behavior model. Step 6, right? You have the discrete event simulation of the crowd, you have the pathfinding, and you have the BDI model's outputs. You feed all these to the behavior model, okay? There's 3 steps in the behavior model. The first one is an emotional elicitation process. This is your basic perception model that determines where the agent is in the environment. And then the second part is your agent-based modeling or modeling of intention. So agent-based modeling could be AMT, modeling of intention could be done using Wasabi or Gamma, right? This is where the bulk of your agent modeling happens. This is where you can switch your plans based on some internal state. So if I'm hungry, I go to a restaurant. If I'm done shopping, I want to grab a coffee, something very simple like that. Or something more sophisticated based on what just happened in the environment. If the escalator is broken, I need to reroute. If there is a special outside a restaurant, I might just grab lunch before, those kinds of things. Okay. But this is all like different behavior. And this is not just individual, this is behavior across the crowd. Okay. You've got the crowd model, and you've got the post identification, and you've got the agent-based modeling, but this is done across the full crowd based on input from the crowd data. So how do you now know what the crowd is doing and what it's up to? If it's being malicious or dodgy, or if it's just regular and benign. That's where the SVM comes in, and that's where the historical training data comes in as well. So you train that machine learning model to look at the agent-based modeling you've done, to look at the modeling of intention and the output from that, and then determine if this is suspicious or not. That's finally the output of the behavior modeling step. And that's a very quick overview of step 7, behavior modeling. Let's start a little and discuss surveillance. Step 8, the surveillance model, is machine learning based. Its job is to detect the faces of individuals in a crowd and extract morphometric vectors from those faces. To do that, it needs 2 inputs: what the crowd model produces as output, as well as video feeds, CCTV from common and restricted areas. If it has these 2 things, right, it needs to recognize individuals, take their faces, correct those faces for perspective, occlusion, lighting, and extract morphometric vectors from that. In order for it to know who those individuals are in a crowd, it then needs to compare that against reference morphometrics that's there in the CBIR biometrics database that we created at the end of step 1. Okay, so that's how it does the matching. If it has the reference and if it has the morphometrics in the image, it can then know who the people are in a particular image. That is a post-processing step. It still needs to know whether or not there is an access control violation. Should that person be in that location? Are they authorized? So that's the final step. Okay. If there is a violation or if there's not a violation, it doesn't matter either way, right? You send this information off to the next stage, which is the preventive security engine. The preventive security engine now has to take that information and perform the action. Maybe it involves a human in the loop in order to vet and check if there truly is a violation. And if there is a violation, then what actions does it need to perform? But that's the domain of step 9, the preventive security engine. So let's see how step 8 is implemented. The first part is a CNN. Okay, it takes the output of the crowd model, it takes the video feeds. Okay, it produces morphometric vectors which are corrected for perspective, occlusion, lighting, and so on. So that's the morphometrics in the image data. You have the morphometrics also available in the CBIR biometrics database that we created in step 1, feature extraction. In order to know who those individuals are, that's part 2 of surveillance. Okay, and there all you're doing is a simple distance measure, right? You are comparing the candidate morphometrics to the reference morphometrics and coming up with a very simple score. Let's say for a particular face, right, there are 4 matches. Ahmed could be 70%, Balaji could be 20%, Kathy could be 6%, and Donglin 4%. A very, very simple sort of match, or very, very simple matches. This information is now compared with access control. Okay, you find Ahmed, yes. Balaji, yes. Kathy, no, she has no access in that location. Donglin, yes. So that's 3 positives and 1 negative. All of this is then fed to the preventive security engine for it to go do its thing. It could potentially involve a human in the loop because, for example, the chance of that particular individual being Kathy is only 6%, and that's small. That might not be big enough for the security engine to perform corrective action on its own without a human vetting it. But all that we'll see in the next step. Okay, this is an overview of how the surveillance system works. And finally, we come to the last step, which is the preventive security engine. So there's 2 things that could happen here. Okay, firstly, the preventive security engine takes input from surveillance, from the behavior model, from the crowd model, okay, and based on certain situations, predefined beforehand as part of policies, as part of procedures, as part of rules and regulations, it would need to react in predefined ways. It would need to enact predefined plans based on rules. So there's one aspect, that's that. There's another aspect where it potentially needs to react to unforeseen changes. Say it's enacting a plan, and for example, an elevator shuts down, or something happens and people just show up in the corridors celebrating something. It needs to be able to react to these things on the fly. So there's 2 parts to it. One is predefined planning, and the second part is reacting to the environment. So let's see how that works, okay? As you can see, steps 1 through 8, as well as 9, this is the technique flow. Everything we discussed so far, all the individual techniques, all listed in this flow. And this ultimately is going to be your blueprint in order to build your prototype, okay? Step 9, the 2 parts. The first part, which is response based on a predefined plan, that would be implemented as part of a rules-based engine. You could just create a rules-based engine that's simple. You could build something that's a little bit more complex, that will require logical programming. But that, I think, depends on the scenario of the building. Okay. The second part, where you are reacting to the environment, in order to accomplish that, you might need a partial order planner to respond to changes in the environment and replan on the fly. So these are the two components that we'll go with as part of the initial build and initial hypothesis for how the preventive security engine should work. And this kind of gives you the endpoint, right? You had the tasks, right? It was very, very high level. And then you had the methods that just talked about each task, how you're going to solve them. But now, against each one of those things, we put a lot more flesh, right? This is a good starting point. In order for you to prototype and go build things, right? You can take these and almost start adding a spec. Your team can take that away and start prototyping the individual parts. They can just start with any configuration or configurations that they are familiar with, right? And as part of prototyping, they'll find, okay, so this is not working, let's tweak this part. And then you'll see that, well, when you're working with that, right, maybe the small tweaks do not help. Maybe that technique is not the right one. Then we swap techniques in, right? We put a different technique into these places. And sometimes you might find no technique does the job, right? Then the whole method needs to be questioned as to whether or not it has a place in the architecture, right? And so that's the second step. Maybe it's even worse than that, right? Maybe it's at a place where the method itself, right, or the flow itself is wrong. Not the method, but the flow itself is wrong. In that case, then you go back to that level and look at it at any stage during this process when you're looking at this, right? If there's prior information and this know-how, insight that tells us that this particular thing is wrong and that's not the right way to do it, but here is the right approach, by all means, put it in, try it. Let the results drive your decisions. As I mentioned earlier in this session, this domain is one where results don't always generalize well, even between problems in the same domain. Sometimes they can, many times they don't. So use results to make decisions and as the foundation in this iterative experimental approach to validate and approve each part of the architecture. If you do that step by step and all of the different pieces are accepted, and then you have global tests where everything comes together and works fine, then you have something that works that can then be used to actually develop the system, to scale it, to performance test it in real conditions, and so on and so forth. Anyway, so this is kind of an overview of the scenario step where we took the method flow and put flesh and skin against it in terms of assigning techniques to each one of those things and as a starting point for prototyping.
Okay, thank you, Jack, for all the explanation and the knowledge once again. Thank you guys also for watching. If you like this video, please don't hesitate to like and share. You can also find our website just below, and don't hesitate to take the test to see how the hero methods can help you. So thank you again and see you in the next time.
Bye-bye.
Ciao.